Swayam Prabha. Digital India. Educated India.
Good morning and welcome back to the course on classics in total synthesis part 1, and we have been discussing total synthesis of various natural products. In the last lecture we talked about the total synthesis of a marine natural product called Eleutherobin, and where we talked about the total synthesis reported by K.C. Nicolau. So today we will talk about another total synthesis, but this time reported by Danishefsky. And in the case of Nicolau's total synthesis, he started with the carbon, the monoterpene, and here Danishefsky started with another monoterpene called alpha philandrine. And his work required lot of stereochemical studies, particularly with respect to carbohydrates, so that he could prove the correct isomer of the final natural product, that is Eleutherobin. And his total synthesis involved 3 important key reactions. One is the Nosaki-Kishi-Hayama ring closure reaction to form the 5-membered ring, and the second key reaction which is also a very interesting rearrangement, that is pyranose to furanose and furan to pyranose. Okay, so these 2 key reactions he had used to first convert the furan ring into pyranose, and then later the pyranose ring was converted into 5-membered furanose ring. The third key reaction was the Stille coupling between the carbocycle and the carbohydrate moiety to form the core structure of Eleutherobin. So, from retrosynthetic point of view, as you can see here, it is very clear. You have a complete carbocycle and a sugar unit. Okay, so the easiest way to disconnect is just you can disconnect either here or here. So, if you are using Stille coupling, then the disconnection of bond A is better than disconnection at bond B. So, the Stille coupling disconnection gives Danishefsky these 2 fragments. On the left hand side you have the vinyl triplet, and the right hand side you have the tributyl tin derivative, which is required for the Stille coupling. So, now for the synthesis of the carbocyclic derivative, that is a tricyclic compound, the triplet can be obtained from this protected alcohol by removal of the pyolide group, oxidation to ketone, and followed by enol triplet formation. One can easily convert this into the required triplet in 3 steps after protection of this hydroxyl group. Now, this 5-membered ring, as I said, this is one of the key reactions where the pyranose form, where the pyranose form was converted into furanose form using acidic condition. This pyranose form again was obtained from furan. So, here using this hydroxyl group, an epoxidation of one of the double bonds of furan followed by the rearrangement, one can easily get this 6-membered pyranose ring. That was the second key reaction, and the third key reaction is the intramolecular Nosaki-Kishi ring closure reaction between this the bromofuran and this aldehyde to form the 10-membered ring. So, now if you look at this, it is very easy. If you have this aldehyde and you can use the lithiobromofuran addition to this aldehyde to generate this chiral center with OH, and for the southern hemisphere you need CH2CHO that can be obtained from this ester by reduction and homologation. Okay. So, now these two substituents on this 6 membered ring can be easily introduced from philandrine, a commercially available monoterpene using photochemical reaction as the key reaction. Okay. So, as I said, there are two key reactions which he has used. At least I will talk about one key reaction, that is Nosaki-Kishi reaction. Nosaki-Kishi reaction is nothing but if you have a vinyl triplet or vinyl halide and this on treatment with aldehydes, in the presence of chromous chloride you will get an allelic alcohol. This reaction can be done intermolecularly as well as intramolecularly. Basically, if you want an allelic alcohol, so this is one of the very important transformations, and one can also get homoallelic alcohol using similar conditions. Here instead of vinyl bromide what you need is an allyl bromide. So, allyl bromide on treatment with aldehyde in the presence of chromous chloride, it gives homoallelic alcohol, and if you have an ester at appropriate place, then the homoallelic alcohol which is formed can also intramolecularly attack the carbonyl group of the ester, forming a lactone. Okay. So, this Nosaki-Kishi reaction has been widely used for making allelic and homoallelic alcohols and also many macrocycles. So, now let us see how Danishefsky's group synthesized eleutherobin, and as I said, the synthesis of eleutherobin requires synthesis of two different fragments, one the carbocyclic ABC ring fragment, the other one is sugar fragment. So, now let us start with the synthesis of sugar fragment, for which he started with the commercially available D-arabinose, and the first step was the per-acetylation, that is all the hydroxyl groups including the lactol hydroxyl group were acetylated with acetic anhydride and DMAP. Then this particular anomeric acetoxy group, okay, can be easily displaced with ethane thiol under Lewis acidic condition, and here you can see the alpha ionomer is the major isomer. Okay. So, once you have that, then the 3 acetates, okay, 3 secondary acetates can be easily hydrolyzed by treatment with sodium ethoxide methanol. Now, if you look at this triol, these 2 hydroxyl groups are cis to each other and these 2 are trans to each other. So, one can easily protect the syn diol to get the corresponding acetonide under standard conditions. Now, what needs to be done is you have to introduce a CH2O SNBU3 and also protect this hydroxyl group. So, these are the 2 things left for the synthesis of sugar fragment with tributyl tin group, which is required for Stille coupling. So, you take this free hydroxyl group, now protect the hydroxyl group as TBS ether, protect the hydroxyl group as TBS ether, then treat this anomeric thioether with tributyl tin methanol, in the presence of methyl triplet. So, that gives you the required, you can see CH2SNBU3. So, here beta isomer is the isomer which is required for the Stille coupling. So, now removal of that TBS group by fluoride reagents like TBAF will give the hydroxyl, and simple acetylation gives you the fragment required for the Stille coupling. Okay. So, now he has synthesized the sugar fragment successfully in few steps starting from D-arabinose. Now, let us look at the synthesis of ABC ring of eleutherobin starting from a chiral monoterpene called philandrine. So, the philandrine, so this is the structure of philandrine. Now, if you look at this structure of philandrine, there are 2 double bonds. One is a tri-substituted double bond, other one is a disubstituted double bond. And as I mentioned when I talked about the retrosynthesis, it involves a photochemical reaction. So, it has two double bonds and selectively one of them has to undergo 2+2 cycloaddition reaction. So, as I said, one is trisubstituted, other one is disubstituted, and between these two, for steric reasons, one can selectively carry out photochemical 2+2 cycloaddition reaction with the disubstituted alkene. The other alkene was the dichloroketene. The dichloroketene can be easily obtained by treatment of zinc with trichloroacetyl chloride, or one can also get it from dichloroacetyl chloride with mild bases like triethylamine. So, now once you do this reaction, what you get is a mixture of two isomers, and once the dichloroketene is formed, because of the presence of the bulky isopropyl group in beta position, this dichloroketene will come only from the alpha side. Okay. So, that is how these two hydrogens, you can see when it approaches from the alpha side, these two hydrogens will be beta. So, this is the major product. Once you have this, the two chlorines can be easily exchanged with hydrogen by treatment with zinc methanol. So, zinc methanol removes the two chlorines. Now, we have to open the cyclobutanone ring. Okay. So, one way is to introduce a functional group here. Okay. You can introduce a functional group and open this cyclobutanone, and if you use Baeyer-Williger oxidation, so then it will open up here, which is not required. You need to open the cyclobutanane at this place. So, for that it is easy to introduce an aldehyde equivalent. Okay, if you look at this, so this is an aldehyde equivalent. If you hydrolyze this enamine, okay, this is an enamine, basically it is a enamine derived from dimethyl formaldehyde, protected dimethyl formaldehyde. Okay. So, now this enamine upon hydrolysis with para-toluene sulfonic acid. So, what will happen? So, you will get first you will get an aldehyde like this. Okay. Then under acidic condition that is with methanol, what will happen? The methanol will attack here and open up. So, that will give you the corresponding ester, that is you will have this aldehyde and ester. Okay. You will have this corresponding aldehyde and ester. Okay. This is the product you get. Is it clear? So, now what you need to do? One, you have to add the furan ring to this aldehyde. Now it is protected aldehyde. Other one, you have to homologate this ester, isn't it? What you need is a CH2 CHO. Already you have CH2 CHO here, but here you have only CO2 Me. So, that should be homologized. Okay. So, first you remove this acetal, okay, para-toluene sulfonic acid and water, you remove the acetal, you get the aldehyde. Now, once you have the aldehyde, take this 2,5-dibromofuran, this on treatment with butyl lithium. So, one of the bromines will be exchanged with lithium to get the corresponding lithio species. This furyl lithium, that is bromofuryl lithium, will add to this aldehyde. So, you have aldehyde and ester, and as you know, aldehyde is more reactive than ester. So, once it adds to the aldehyde, so what you get is a mixture of this alcohol, which is as a result of direct addition of this lithio species to the aldehyde, and the second product is nothing but this alcohol attacking the ester carbonyl and forming the 6-membered lactone. Okay, so these are the two products, and the major product is this alcohol. Okay. So, now you have the alcohol, next step is to protect the alcohol. So, the alcohol could be protected as TBDPS ether under standard condition. Then now you need to homologate this ester. Okay. How do you do? Okay, you have to first reduce, then that CH2OH should be homologate. So, the reduction is normally done with diol. If you use excess diol, you will get the corresponding alcohol. So, here they use excess diol, so that you get the primary alcohol. Now the primary alcohol can be homologated through methylation. So first you methylate the primary alcohol to get the methylated compound. This upon treatment with potassium cyanide. Okay, this is a good leaving group, methylate. So now if you treat with potassium cyanide in the presence of 18 crown 6 ether, you get the corresponding cyanide CH2Cl. Okay. So what we need now, this cyanide should be reduced to aldehyde, then the intramolecular cyclization should take place. Okay. So diol reduction of cyanide will give you aldehyde. So that was a very clean reaction. Then the second key reaction. Okay. So the second key reaction in the total synthesis of Danishefsky is the Noshaki-Kissy reaction. So this upon intramolecular Noshaki-Kissy reaction gave the corresponding 10-membered ring wherein the alpha isomer was the major product. The hydroxyl group, which is alpha, is the preferred product, which you can see they got 15:1 ratio of alpha and beta alcohol. Okay. So now if you look at this particular structure, you have the 6-membered ring in place, the B ring, that is the 10-membered ring is in place. Now what you need to do is you have to convert this furan. One, you have to get a double bond here, you have to introduce a methoxy group here, and you have to introduce a methyl group. So 3 things one has to do. One, introduction of methyl group, introduction of double bond, and introduction of methoxy group here. But at the same time you should know these 2 double bonds should not be there in furan. Okay. So what did they do? Before you do this, you need to protect the newly formed hydroxyl group. Okay. So that was protected as bivalate ester by treating with bivalyl chloride. Then you can remove the TBDPS group. Okay. So standard TBAF, tetrabutyl ammonium fluoride treatment will remove the TBDPS to give the corresponding alcohol. So once you have this alcohol, if you look at the relationship between this double bond and this hydroxyl, it is an allelic alcohol. Okay. That hydroxyl group will direct the incoming peroxidizing agent so that you will get alpha epoxide. So what happens once you treat with dimethyl dioxide DMD, you get the corresponding pyranose ring. So not only epoxide is formed, it undergoes a rearrangement. Okay, it is a well known rearrangement to form this hydroxypyranose. How does it happen? It is very simple, it is well known in the literature. So first, as I said, it forms the epoxide of the double bond which is close to the hydroxyl group. It is like allelic alcohol epoxidation. Once it is formed, then you can see the arrows, the opening of this 5-membered ring gives rise to this ene-dione. Okay. It is basically nothing but if you have 1,4-diketone on treatment with acid you will get furan. Okay. 1,4-diketone, if you treat with acid you will get furan. The same thing, it is a reverse reaction, but since you are using oxidation you get extra double bond. Okay. It is just a reversal of acid treatment of 1,4-diketone to furan. Here what you are doing is you are using an oxidizing agent, so that is why you introduce a double bond as well. Once this ene-dione is formed, then intramolecularly the hydroxyl group here will attack the ketone to form the 6-membered ring. Okay. So what you have done now, you have oxidized the furan ring, and while doing that it underwent a ring expansion reaction to form a hydroxypyranose. Okay. And this is also good in one sense that if you look at the natural product, you need to introduce a methyl group here. So now this has become easy because you have an enone. Okay. You have an enone, then it should be easy to introduce the methyl group here. So how did they do? First you protect this lactol. Okay. So, protect it as TMS ether, then you add methyl lithium. Okay. So, methyl lithium addition to the enone comes from alpha side, that methyl group comes from alpha side to get the beta alcohol, then you treat with acid. Okay. Here when you treat with acid, this pyranose ring rearranges back to the furanose ring. Here the pyranose ring rearranges back to the furanose ring. So, how does it happen? This is a very interesting, again a rearrangement, it is like shuttle trip rearrangement. Once it was 5-membered ring, that is furan, furan to pyranose, now pyranose to furanose. Okay, it is like shuttle trip rearrangement. How did this happen? The moment you protonate, what happens? This oxygen gets protonated, then this lone pair on the OTMS opens this. So, what you get? This oxonium ion. Okay. Now, if this hydroxyl group attacks back, if this hydroxyl group attacks back, you get the same pyranose ring. Whereas, if this tertiary alcohol attacks this carbonyl, then you will get furanose ring, isn't it? So, that is what happens. Here the tertiary alcohol attacks the oxonium ion carbon to get the 5-membered ring. So, now this is very easy to see all the functional groups required for the synthesis of eleutherobin is in place. You have a hydroxyl group here, okay. Then the OMe is there, methyl also, and what you need to do is you have to convert this into enol triplet, and also the northern hemisphere hydroxyl group you have to esterify. Okay, these are the two things he needs to do to complete the total synthesis of eleutherobin. Okay. So, what did he do first? He protected the hydroxyl group. Okay, he protected the hydroxyl group as TBS ether. Okay, so that he can remove the pivalyl group and make it as vinyl triplet and then couple with tributyl 10 derivative of the sugar to attach the sugar fragment. Okay. So, you protected the hydroxyl group, then you reductively remove the pivalyl ester. So, pivalyl ester can be reductively removed because it is an ester, is not it. So, if you reduce with dibol, the pivalyl ester gets cleaved and then you will get the hydroxyl group. Hydroxyl group was then oxidized with tetra N propyl ammonium perruthenate TBAP and NMO to get the ketone. So, once you have the ketone, the next step is to make the enol triplet. So, this was successfully done by making the enolate with lithium hexamethyl disalicide, and the triplet was introduced using well known Cummins reagent. Okay. So, now the enol triplet is made. So, that means the whole carbocyclic core structure of eleutherobin is ready, and already we have discussed the synthesis of sugar fragment. So, what we need to do is we have to couple this triplet with the tin derivative using Stille coupling, and the Stille coupling worked very well with tetrakis palladium to give the complete structure of the eleutherobin. So, what is left now is you have to remove the TBS, attach the side chain, then remove the astronide and acetyl group. So, these are the three things left for the total synthesis of eleutherobin. So, first easiest is to remove the TBS group. Okay, treatment with TBAF, you remove the TBS. Next, you have to attach this side chain. Okay. So, this alpha beta unsaturated acid is a known compound, and now using DCC you can couple this carboxylic acid with the alcohol to introduce the side chain on the northern hemisphere. Okay. Now, what is left? You have to remove the acetate and you have to remove the acetonide. Okay. So, both are done in one step. Actually, if you look at the eleutherobin, this acetate is intact. Acetate is required in eleutherobin. Only you need to remove this acetonide. Okay, you have to remove only the acetonide, and that was done easily by treatment with PPTS methanol. You remove the acetonide and that gives eleutherobin. So, that is how he could complete the total synthesis of eleutherobin. And if you look at the total synthesis of eleutherobin reported by Danishefsky, so he started with 2 commercially available as well as naturally occurring compound. For the carbocycle, he started with a monoterpene called alpha philandrine, and for the sugar fragment he started with D-arabinose, a commercially available sugar. Okay, Then there are 3 key reactions which he used. One, the Nosaki-Kishi reaction to form the 10-membered ring, and then second, the ring expansion of furan ring to pyranose, and the third one is the pyranose to furanous, that is 6-membered to furanous 5-membered ring was done under acidic condition. There is the 4th key reaction, that is that still a coupling between the carbocyclic triplet and then tributyl tin derivative of sugar fragment. Okay. So, these are the 4 key reactions which Danishefsky used to synthesize eleutherobin. Overall, this total synthesis was accomplished in 26 longest linear steps and with an yield of 0.25%. So, considering the molecule, considering the complexity of the natural product, 0.25% overall yield is really a healthy one. Okay. So, this way if you look at the 2 total synthesis which we have discussed on eleutherobin, Nikolow's total synthesis and Danishefsky's total synthesis actually involved some key reactions, and also new chemistry were developed during these 2 total synthesis. Okay, thank you.